An introduction. Quantum is often associated with weirdness, but it helps us understand the universe fundamentally, because quantum particles make up everything around us. The word quantum represents discrete, like the shells of electrons. Quantum computing is therefore using quantum weirdness to make calculations. A discrete bit of quantum information is called a quantum bit or qubit. Qubit's special property is that it is uncertain before being observed. In this case, observation is any sort of interaction. A qubit can be a merge of 1 and 0. When a coin hasn't landed, heads or tails are equally likely. It doesn't choose, it is both, because both are equally valid answers. Seen on a visual aid such as a block sphere, it allows 1, 0, and anything in between. Because of this, qubits information is exponential, 2 to the power of n amounts of information for a number of qubits. Therefore, quantum computers are better at simulating complex systems, because chemical systems increase in complexity in the same way qubits does. Prerequisites. To deeply understand quantum computing, you need knowledge of basic quantum mechanics, linear algebra, basic abstract algebra, specifically group theory for working with the symmetries of spin, as well as probability theory for qubits are probabilistic, stochastic processes, Fourier transformation, algorithm analysis, and finally, the Python language is used to program the quantum computers. Schrdingers Cat and Superposition. When we send electrons through two narrow slits, electrons act as waves and interference is observed. When observed, however, it becomes a particle. The Schrodinger's cat is a famous analogy for objects being in a wave-like state before being observed. Continuous waves hold more information than discrete points, making quantum computers powerful. In other words, quantum and classical computers have the same input and output. It is a process that proves quantum computers to be superior. Chemistry of quantum computers. Some processor insights. Superconductors are materials with no resistance to electricity. Lanthanoids in orange are used, with their uncertain electron acting as qubits. Because of current computer advances, silicon is also widely used as a semiconductor. In this D-wave chip, niobium loops are used as qubits. When cooled down to 9.7 kelvins, niobium becomes a superconductor and exhibits quantum effects. This is Google's Bristlecone chip. When a charge is sent through, calculations are performed. This is then a qubit where niobium is placed in a loop. 1 and 0 is clockwise or counterclockwise flow of electrons. But electrons here are special. They are waves that flow in both directions. This allows any point on the block sphere to be mapped just by changing the controls. For many qubit interactions, the loops are stretched into rectangles, lying grids like this in the Bristlecone chip. This is a complex grid layout and circuit operations, which are all controlled by a classical computer using microwaves. Seen in these room-height D-waves computers with their classical interface, it is large because most components are made to protect the qubits. Quantum decoherence. Decoherence is a prominent problem in quantum computing that destroys qubit states. Examples of disturbances are radiation, vibration, and temperature. As seen here, through decoherence, a special qubit collapses down to a normal bit. It is a main reason for quantum computers' size. Most mechanisms aren't built for calculation. Dilution refrigerators. Because the temperature kicks qubits out of superposition, it needs to be reduced down to absolute zero by refrigerators, only possible currently with a spacious design. The helium refrigerator uses a U-tube and a dilution between helium isotopes. The mass differences between helium-3 and helium-4 dilution captures enough heat for the final push to 0.2 Kelvin, as Professor Morello puts it.
By helium-3 from here, you will have new helium-3 atoms that can jump into the helium-4 phase. And as they do so, they actually absorb heat. Because the entropy is increasing when you take atoms from a pure phase into a dilute phase.
And this is a general diagram for any quantum computer. Molecular qubits. Previous qubits are electrons, atoms, or photons. But another way to reduce noise is to choose the better type of qubit. Researchers at MIT proposed a molecule of potassium and sodium acting as a qubit, and their different symmetry proves beneficial over a single atom, such that they can more easily vibrate and rotate with handles for manipulation. This provides more ability to overcome the chaos from noise. Gold. This is an iconic picture of quantum computers. Most of it is not what meets the eye. Unsurprisingly, only a small fraction of the space is the actual quantum chip. The rest is spacious design accommodating refrigerating cryostats. From the dazzling golden appearance, it is obvious that the precious metal is used. Gold is used to prevent qubits from overheating, like in this trip from Rigetti, allowing qubits to last longer and travel farther. Extensive shielding. Noises like magnetic and radiation cause decoherence, so a spacious shielded room and tube are designed to block the noise. The 16-layer outer shield room creates a low magnetic radio environment, made of metals like copper and aluminum. The inner tube blocks radiation and holds vacuum chamber, made of lead or concrete.
Inside that system is a thumbnail-sized quantum processor,
which lies at the end of the whole apparatus. As a description from D-Wave shows,
the main room behind us houses the quantum processor, and the data racks in the front hold the quantum server where users can access and program the quantum processor. And the other data racks include the cooling system, which includes pumps and is responsible for the chirping sound you can hear in the background. Inside the room, before we get to the quantum processor, there are many layers of shielding which allow us to create the low noise magnetic environment the chip sits in.
Error correction. Noise is not completely removable, but information can just be repeated to serve as backups. It is then predicted that we would need 1 million qubits to combat errors. Rose's law therefore states that quantum processing power doubles every year, so it should only be a few decades away. Their future significance. When an electron is 50% here and 50% there, it is possible that two universes exist, but when observed, only ours showed up. Thus, operations are performed in both at the same time. This allows them to deal with emergent properties that baffle classical algorithms in computers, such as finding a number in a large list with only the square root amount of normal time, using the gates of quantum computing. But as of now, algorithms are more advanced in hardware, because apparently advances in hardware are too slow. Yet, once the hardware catches up, they will be able to succeed in the following. Enable us to simulate chemical reactions, as adding an atom doubles the complexity, just like how qubits work. Simulations quicken drug development and battles cancer. Optimizes traffic flow. Breaks encryption by quickly factoring large numbers. Finds the shortest optimal path through complex systems. Emulates the brain to achieve artificial intelligence. Predicts the market demands and niches. Accurately forecasts the weather. And allow human-computer symbiosis, thus making way for rapid scientific advancement and ages of cognitive renaissance. As of now, companies like IBM, Google, Intel, Microsoft, and Alibaba are pioneering in quantum computing, so it will just be a matter of time. Thank you for watching.